What's up? So today we're gonna solve in the code 150 heap slash priority queue. Great pyramid get trees, tries backtracking, and now we're at final part of the heap slash priority queue. Let's no. Stop. No. Over. Right, I'm back. Okay, let's continue. Oh, God, this is gonna be the last. Hey, stop. Last. Have to watch one. Okay. Hey, that's 56 seconds. Stop it. I saw that. The median is the middle value in a sort list of integers. For a list of even length, there's no middle value. So the median is the mean of the two middle values. 1, 2, 3, median is 2, 1, 2, 1.5. So this is 1 plus 2. So the idea is, and then call the level. This one, two, one. So that, so we're gonna create a class that finds the median. Oh, self dot void addnum. This one, double find. So median of all. So median finder, no addnum, no one, no find median, no addnum, two finder addnum. Okay, so uh, addnum one, find median. Wait. This one is this one. Unknown is this one. Oh, still confused. Okay, so addnum. And then this is the parameter. Find median that addnum three. Find median again. Addnum two. And find median again. Same person. Yep. Start the speech you recite. Check by me. A better question that sufficient that we're gonna use Q's. Yeah, maxHeap. Oh, it's interesting. So each time uh maxHeap super you want to give Q first. It's the same Q. It's what perfect. Right? So so for solutions, this is a hard one. This is to sort this solution as well. There's a lot of functions, but this is
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve find median from a data stream. So this is another hard problem, but it's not super difficult if you know the data structure behind it. So they basically tell us we know the median is defined as the middle value in a sorted integer list. If the list is even, there is no middle value, so you take the average of the two middle values, right? So with this sorted array, the middle value is 3, so the median is 3. With this, there is no middle value, so you take the two middle values, add them together, divide by 2, and then you get a median of 2.5. And so we're actually designing a data structure that's going to have two operations. One operation is going to be adding a number to our data stream. So we actually have to store the list of numbers, and that list of numbers is not constant. It's going to be changing every time add number is called. And then from that list of numbers that we're going to be maintaining ourselves, we are going to need to constantly be finding the median of that list. So every time
yep.
this function find median
I
is
don't know
called,
how
we
to
have to return what
use
the
actually
median.
the median finder though. But I can say self dot. Wait. Yeah, and it's an array. Cause also be a heap. All of them. Is this faster? What's this solution? It used, I don't know,
Hey everyone, welcome
two
is in
heaps.
sorted order. Hey everyone, from that list of numbers that we're going to be maintaining ourselves, we are going to need to constantly be finding the median of that list. So every time this function find median is called, we have to return what the median is from the elements so far. So this is just an example. If we add num1, then our list is going to have 1 in it. If we add another number 2, then our list is going to have 2 numbers. Then if we want to find the median, we will take the average of these two, and it's going to be 1.5. After that, we'll add another number, 3, and then we'll find the median again. In this case, the median is different because our list got updated. The middle value is now 2. So what's the most obvious way to solve this problem? Well, I basically just hinted at it, right? So the obvious way to solve this is insert elements in order. So let's say these are the function calls that are going to be made. So we're going to add 4 numbers and then we're going to try to get the median. So we're going to maintain a list or an array, right? And every time we get a function call add 3, we're going to insert in order just like it says up here. And basically, if our array is always sorted, then it's going to be easy to identify the middle number, right? Which is going to be the median, right? So the median is always going to be in the middle position. And if our array is sorted, we'll always know where that is. So the first one we have is add 3. So just add it to the first spot. Next, we want to add 2. So how do we do that in order? Well, we have to traverse our array so far. So we see that there's a 3 over here, right? So then we got to replace that 3. We shift the 3 to the next position, and then we put a 2 in the position that the 3 was initially at, right? So now our array is in sorted order. We had to shift some elements, and we had to search for the spot that we put the 2 in, right? So you can tell that every time we add a number, it's going to be an O of n operation, where n is the number of elements we have added so far. So we added 2. Next, let's add 1. Well, we're going to traverse the array, right? We're going to see, okay, the first element is 2. We know that 1 is less than 2. So really what we're going to do is cross out the 2, cross out the 3, right? Shift the 2 over here, shift the 3 over here, and then put a 1 here. But I'll just, to keep the picture simple, I'm just going to put the 1 over here. But we know that in the worst case, every time we insert an element, it's going to be O of n. Lastly, we're going to take the 4 and add the 4. So we're going to see 1, nope, 4 is bigger than that. 2, nope, 4 is bigger than that. 3, nope, 4 is bigger than that. So we add the 4 at the end. So now we finally have a getMedian call. Well, good thing for us, since our array is in sorted order, we know getting the median is super easy. In this case, we have an even length list, right? We have 4 elements, so we are going to take the 2 middle elements, 2 and 3, add them together, divide by 2, we're going to get 2.5. So we know that the getMedian operation is always going to be O of 1, but adding a number is always going to be O of n. So how can we speed this O of n operation up? And let me just tell you, basically what we're going to do is, instead of having just a single list of elements, we're going to break this up into 2. And we're going to have basically 2 subsets, right? And 1 is always going to be less. So this has 1 and 2, and this has 3 and 4. And all elements from the left are always going to be less than or equal to all elements in the right. So this will also make it easy for us to get the median. But I'm not just going to have arrays. I'm going to use a heap or a priority queue. So we're going to use a heap data structure. So I'm going to have 2 heaps in this case, a small heap and a large heap. Small heap, all elements in the small heap are always going to be less than or equal to all elements in the large heap. Also, the size of these heaps is always going to be approximately equal. So if there were 2 elements in this heap, then there has to be 2 elements in this heap. What if we had an odd number of elements? So what if there were 3 elements in this heap? That's allowed because we know that we can't actually have these be equal if there's a 2 and a 3, right? Or in the opposite case, there could be 2 elements here and there could actually be 3 elements here. That's also allowed because we know that's approximately equal. If the difference, though, is ever greater than 1, so if there were 4 here and 2 here, we know then we have to balance them, right? Make this equal 3 and make this equal 3, right? We always have to keep it as balanced as possible. And if you're not familiar with what exactly a heap is, it's basically like a list. It's pretty similar to a list. It's implemented using arrays or lists. The only difference is, though, adding a number, we don't add at the beginning or at the end. We just add elements to the heap, and adding an element to this heap is always going to be a log n operation, and removing an element is also going to be a log n operation, right? So add or remove is log n. And there happen to be 2 kinds of heaps, a max heap or a min heap. And the thing about these is, so for a max heap, finding the max in this list, so find max, in a max heap is always going to be O of 1. So that's the advantage. We know that finding the max in a regular list is O of n because you have to search the entire list, but with a heap, we can find the max in constant time. Similarly, with a min heap, if you want to find the min, that's also an O of 1 operation. So with that being said, the small heap is going to be implemented as a max heap. And the reason we have a max heap and not a min heap, it's kind of counterintuitive, right? If this is the small heap, why are we using a max heap? And for this one, we're actually going to have a min heap instead of a max heap. And the reason
Really
is,
weird
what if
math.
we had elements to
Right? Right.
these heap, and for this one, we're actually going to have a min heap instead of a max heap. And the reason is, what if we had elements to these
Look at this.
heaps such as, right? What if we had these elements in each of the heaps, right? We see that all elements here are less than or equal to the elements in the right heap. But if you actually want to find the median of these, we know we need to get the max value in the small heap, right, 2,
The
and we need to get the
value in the
min
large.
value in the large heap, 3,
Oh,
add them together, and then
sure,
divide by 2, right? That's how we're going to get the median. So that's why we need the min heap, right? We always want the minimum value from our large heap, and we always want the max value from our small heap. And of course, finding the median like this way, right, getting the value from each of the heaps, it only works if the size of the heaps is approximately the same, right? If in this case they're equal. But what if we had a third element in this heap? What if we had a 3? Well, they're approximately equal, right? But you can see the length of this one is greater, right? But the difference in length is 1, so they're approximately equal. In that case, how are we going to find the median? Well, since we know that the length of this heap is bigger than the length of this heap, we know that we have an odd number of elements in that case, right? If one heap is bigger than the other, there's always going to be an odd number. And in that case, we're going to want to get the value from this heap. So if the length of this heap is bigger, we're going to want to get the max from here. We're going to want to get the max value from this heap, and that's going to be 3, and we know in this case 3 happens to be the median, right? Because look at them, these values are in sorted order. We get rid of these 2, we get rid of these 2, the middle value is 3. And I'm not going to walk you through this case, but let's just say, imagine we had a 2 over here. The exact same thing would happen, right? We would get the min value from here, we get the 2. And notice that, look, the max value from here and the min value from here are equal, right? That's why I say every value in here has to be less than or equal. It's possible that they are equal. Okay, so now let me just go through a quick walkthrough of this code again. So what we're going to do, add the first element, which is a 3. Which heap are we going to add it to? In this case, it doesn't really matter. So what I'm going to do is just by default add it to the small heap. So let's add 3 to the small heap. And we know that that was roughly a log n operation, right? Next, let's add 2. So by default, I'm always going to take whatever element we add, and I'm going to take it and add it to the small heap. Now I added 2 to the small heap. But wait a minute, now the heaps are not approximately equal. This has a length of 2, this has a length of 0. It was okay when this had a length of 1 because that's still approximately equal, but 2 that's too big of a difference. So now what we're going to do is find the max value in this heap and add it to this heap, the large heap, which is always going to have elements greater than or equal to the small heap. So we need to get the max value from this heap, and since this is a max heap, actually finding the maximum is an O of 1 operation. Now the downside is we have to remove that value, which is a log n operation. And we're going to take that element that we removed and add it to the min heap, and that's also going to be a log n operation. We know adding and removing from heaps is always log n. Finding the maximum in a max heap is O of 1. Finding the minimum in a min heap is also O of 1. Okay, so now we did add 3, add 2. Now let's add 1. I'm going to change this add 1 to a add 7 just to illustrate one last thing about this algorithm that we're going to do. And let me just cross this out. We're not doing insert order anymore. We're doing the heap solution. So we're going to add 7, right? By default, I know that I'm adding it to the small heap. So what am I going to do? I'm going to take 7 and add it to the small heap. Now, the size of this heap is 2. The size of this heap is 1. So they are approximately equal. The last condition, though, is every element in the small heap less than or equal to every element in the min heap?
Yeah,
Now,
but
how are we
this
going to
one.
check that? Well, we can find the minimum of the min heap in O of 1 time, right? It happens to be 3. We can find the max of the small heap in O of 1 time. It happens to be 7. Is 7 less than or equal to 3? No, it's not. So what are we going to do? Well, we're actually going to do the exact same thing we did before. So I'm going to find the max from the small heap in O of 1 time. I'm going to remove that max. So 7 is removed. To remove, we know it takes log n time. And then I'm going to add it to the min heap, which also takes log n time. So now I'm adding 7, and the lengths are approximately equal still, right? This has 1 element, this has 7.
Yeah, but
In O of 1 thing, it's not. So what are we going to do?
yeah, it checks the
Well, we're
value of
actually
the
going to do the exact same O of move, and the lengths are approximately equal still, right? This has 1 element, this has 2 elements, and now if we get the maximum from here, 2, and we get the min
so it
from
has to
here,
move.
3, we see
Now
that
it's
the condition
unbalanced, so
actually
it has
now
to
is
move back
true.
to
Every
the small
element in the
heap.
left is less than or equal to every element in the right.
So let's
Now we
check.
add our equal condition. Stop this, and we have to move it to be
Now it's
log n,
unbalanced.
and adding it to this one is greater. What are we going to do? We're going to find
The
the min
minimum.
O r approximate. Also a lot more efficient. Now, the only thing we have to do is get the median. And the time complexity maximum from our left heap, which is 3, right? We know we can do that in O of 1 time because this is a max
X
heap.
equals,
We want
just
to
get
find
the
the
max
minimum
in the
value
left.
from our right heap, and we know we can do that in O of 1 time
Oh,
because
it's
this
even,
is a
so
min
just get the
heap. And we
3
know
plus
that
4,
4
7.
happens to be the min value.
Divided by 2.
So we get these two values, 3 plus 4,
3.5.
add them together, divide by 2, and that's going to be our median. So we can still find the median in large and small. Large is going to be a min heap, small is going to be Python. You can add on sensations to q.heap push. This is how you do it in Python. Other languages might be different, obviously. So to the small heap, we're going to push num. Now, Python is kind of annoying in that it only implements.
This one's different. This one is checking if it's self.large and the number is greater than self.large at index 0. And if it is, then we should push it to the min heap. And else you will push it to the max heap. And since max heap is base, there's no max heap on Python. We basically make it negative. Multiply that by the norm. Negative 1 times norm, that would be negative 5. So I we can find the max heap there, which is the lowest. It's pretty weird. So like shooting for the max heap there would be negative 3. Should be weird. Actually, no. Small would be max heap. Yeah, so we would get the minimum value. And this one's different, but I think I can manage with just following this tutorial. I don't know what an API is.
Min heaps, we know small is actually a max heap. So to get around that, what I'm going to have to do is take every number and actually multiply it by -1. This allows us to actually implement a max heap, which isn't implemented by default in Python for some reason. But what I'm doing here is taking num and adding it to the small heap, the max heap, right? But now we want to make sure every element in small is less than or equal to every element in large, right? So every element in the small heap has to be less than or equal to every element in the large heap. So I'm going to make sure that that's true. So if small and large and multiply it by -1 and get the true value that we actually added to the heap. And so I want to know, is this value somehow greater than the smallest value in our large heap? How can I get the smallest value in our large heap? I can do the exact same thing, index of 0. But I didn't have to multiply this by -1 because
There's
this
a
is a
minHeap.
minHeap, and that's what Python does by default. Pop, so I'm going to pop from our small heap. I'm going to get the largest value from our small heap, store it in val, and then I'm going to get the largest value from our small heap, store it in val, and then I'm going to push that value to our large heap. So to our large heap, I'm going to push that value. Basically exactly what I did in the a little nicer. So dot, and then I'm going to pop from our small heap. I'm going to get the largest value from our small heap. Sure, but maybe the code is a little confusing. Oh, and actually, since we know every value pushed to the small heap is being multiplied by -1, to reverse that, we have to also multiply by -1 when we pop from it. Because look, when we put it's annoying because there's no way to really get uneven size, we actually mean a difference greater than 1. So if the length of small is greater than the length of large plus 1, that means large heap is greater than the length of the small heap plus 1, meaning the difference is 2 or greater. And in
this one's bigger, you just take off it and put in val and push it to the
that case,
large.
I'm basically going to do the opposite of what we just did up here. So let me copy and paste that. So we don't need this -1 because we are going to be popping from the large heap, which has, and if there happens operation, we know that then we have an odd length, right? Because maybe one of them has 3 elements, the other has 2 elements. We know small happens to be true if the length of large is somehow greater than the length of small. We know that the opposite happens to be true, so we can return the smallest value in large. Now, if neither of these evaluates, that means we together and then divide by 2 and then return the result of that. So here,
Wow, that's so interesting. So what index 0 somehow gets I think it's because maxHeap based on negative. So so that's sorry.
together and then divide by 2 and then return the result of that. So here is the final code. It's 34 lines.
It's really different. Okay. So first we need to oh, keep push. So that's one. Um, oh, and we're supposed to after that we're supposed to like basically I don't know. Yeah. Shoot that's one. Oh, that's simple.
Hey, every places, so let me
Self, but if it's self as small and large, so there's something. Make sure every node small is greater than or equal to every node large. Make sure that nothing and small. An index of so this is a max -1 times self at small since that's the max heap of index 1 or 0 Okay, it's less than so, checking at 0. There, q dot pop. File. You're supposed to keep up the self dot store. Uh, this, wait, I think I got it all.
self dot.
And it's correct. But we forgot to put the negative 1 times. And we're gonna hit q dot push self dot large to 5. Okay, so this one checks if the num max makes right now. Let's check if the it's best also it's less than large. So we can imagine that if we put 4, since it's defaulting it to push as small, it first checks if it's supposed to be in that small. It's a different solution to this one, which it first checks if it's self that large, else if it's not, we defaulted this one, and immediately do that. But like, it's pretty weird though. But okay, this this one basically checks if it's self that large. No, no, it's self that large. So basically, it checks first if self that large has something. If it doesn't have something, then just at the slot. And it also, I don't know, this one basically is the second one. So it checks if it's balanced. It needs to be a correct so that this it has to be a tree. So right, length of some small, so that small, right? For some that small. Yep. Yes. Greater than length. So large. Then we append the bottom smallest. -1 times just the same idea again, as you can see. It's the same idea. You keep up there. Keep up. This stuff that's the the latest ones that's appended, and you put it in cloud, and you keep queued up. Keep push it to uh stop large. Use about step parameter to be inserted. Okay, that seems correct. And also checks if 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 the balance is different. So if it's less, no. Pretty sure that's no, it's not correct. Yeah, we can also do that because it's also the same. this set over one. So large and so, and don't forget the this one. This one. And see
Opposite happens to be true. One last thing I forgot.
it's still not one down the bottom. It's pretty weird, but yeah, I know it. There should be big plus one because we're fine with like I know we're fine with it being approximate. So that is if this one is two greater, so if like let's say um, this is two and this is one, so if it's one plus one, well it's not greater than it, so that means it's not gonna do this. But once this one got too big, so let's say it's three and this is one, one plus one is two. That means that's now unbalanced since this one's too big by two, so basically even it out. And after that, I think we're pretty good now. Then we can now finally do the third method or function inside the class, which is find median. In this one, you basically check in the odd, the middle, even the center. And first, of course, we gotta first find that it's, if it's this one's larger, that means that's the median, and if this one's larger, then the minimum one is the median. If you get what I mean, right? Sorry, set it clear. So, so it's 7 here. Since it's already properly fixed from this code over here from the addnum, right? Oh, thank you for talk about that's it's really like from some March, not file the actual 10 since
Hey,
so so that's by 0 since this may get is another statement. What did mine use? And there's nothing else. Uh-huh. So 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 and don't have the else else taken. Or you just immediately recheck as well. It doesn't have to have well we cannot have else. Then so long next 0 plus so not large 0 by for the measure.
we have some comments and some
And
largest value.
yeah, just one. And I'm pretty sure this is correct now. Let's see. Oh, see. Swap. See the problem? MF no. Swap. Oh yeah, that,
Hey, remember, small has negative. We multiply the
oh, he forgot to put it. Okay, that's fine. I actually thought there was something wrong with this. This is a site defined side of class. And this should be correct now, but there should be something wrong. Can expect one. Okay. Oh, something wrong.
Hey, I forgot is remember small as negative. We multiply the numbers by negative, so when we're getting the number and actually trying to calculate the median, we have to take that number and multiply it by -1
Oh yeah.
before we add it
And this
to
one as well?
this number and then divide by 2. And let me not forget to do the exact same calculation when we're returning the
This one?
value.
Oh, and that's an honest mistake then. I thought it was already fixed, so that was my bad. It's also not fixed, so yep.
Here, right? So
And it should be there. Finally. Oh hell nah.
error. I somehow had too many bugs in here, but okay, so now finally, this should be the final code when we're returning the value here, right? So I somehow had too many bugs in here, but okay, so now finally, this should be the final code. The big thing in Python, at least, is to remember these -1s. If you're doing this in C++ or Java, I'm pretty sure you will not have to worry about that. This should be the final code finally, and you can see, yes, it is.
Oh, what did we miss? Maybe it should be else. That should be this one. My output is 1.0, but I expected is 2.0. Ah, still remove this one. This should be fine. The else doesn't do anything else. Oh, um, so does it do anything? Oh, wait. Seems to be correct. Which I know. Still wrong.
Hey, getting the number and actually trying to calculate.
It seems we might have 8 that are wrong, I know. The if statement of this doesn't really matter. Shouldn't be lf. Ah, still wrong. Could be wrong.
Calculate the median, we have to take that number and multiply it by -1 before we.
Yeah, 2 doesn't do anything. Or am I missing something? Oh, oh my god. It's a maxHeap. As well as a half maxHeap, so we shouldn't forget making it negative since there's no maxHeap in Python. Oh my god, brother. Oh, that's bigger. It's wrong.
Say, calculate the median, we have to take.
There's no end. Yeah. Ah, there's a problem here. And should be correct now. Lord. Still wrong. There be something wrong? Seems correct.
Hey, median, we have to take that number and multiply it by
Okay, forgot this now. Yeah, we're gonna send it now.
-1 before we add it to this number and then divide by 2. And let me not forget to do the exact same calculation when we're returning the value here, right? So I somehow had too many bugs in here, but okay, so now finally this should be the final code.
Oh, there's something wrong. Oh, there's something wrong. That's fantastic. What's wrong? No, not the heap you import. Oh, oh my, is this one? That's so weird bug. Yeah, there's something to also this. Oh, that's hard. So it's dumb. Okay then. Anyways, thank you for watching. That took a while.